Welcome to a new episode of KEMIA.nl, Chemistry 101. In this episode, we'll be reviewing a galvanic cell, which is an electrochemical cell that converts chemical energy into electrical energy through a spontaneous redox reaction. Here we see a schematic picture of a Daniell cell. A Daniell cell is an example of an electrochemical cell, and you'll probably see a real-life demonstration of this experiment in your classroom. With an electrochemical cell, an electric current is generated. That is why at the top you see a voltmeter, which could also have been a light bulb or an ammeter. In this setup, we'll be generating an electrical current by means of a redox reaction. Let's review the parts. On the left, we have a rod made of zinc which functions as an electrode. It is partially submerged in a solution of zinc chloride. On the right, a copper electrode is submerged in a solution of copper chloride. At an atomic level, we would see zinc atoms in the electrode because zinc is a metal, and metals are made up of neutral atoms. In the solution, we would see zinc 2+ ions and -1 chloride ions. Because the salt is dissolved, the atoms are separated in individual ions. These ions are depicted in white and green spheres. Similarly, on the right-hand side are copper atoms in the electrode and copper ions and chloride ions in solution. Furthermore, we see a salt bridge, which is an inverted U-tube filled with a sodium nitrate solution. The solution is made into a gel so that the solution won't flow out of the U-tube once it's turned upside down. As in a normal redox reaction, the strongest reducing agent would react with the strongest oxidizing agent. In this example, zinc atoms will be oxidized to zinc 2+ ions, producing 2 electrons each. These electrons travel through the wire to the right side, where the copper ions gain 2 electrons each, reducing the copper ions to copper atoms. The reducing agent zinc and the oxidizing agent copper ions react separately. The transfer of electrons thus produces an electrical current. Let's zoom in to an atomic level and see how this process takes place. We'll start by zooming in on the left side at the zinc electrode. The zinc atoms are depicted by gray spheres. These atoms are oxidized to zinc 2+ ions, depicted as white spheres. The electrons stay behind in the electrode and subsequently travel to the right side of the galvanic cell to reduce the copper ions. The electrons leave and the zinc ions go into solution. After a short time, the solution will contain more zinc ions. This creates a challenge which we will look into later. This zinc electrode will slowly reduce in size. Let's take a look at the right side of the galvanic cell, where the copper ions are being reduced. The electrons travel to the right side, where the copper ions in solution take up these electrons. Let's zoom in at the copper electrode. Here, we see the electrons arriving in the copper electrode, and the copper ions in solution travel towards the electrode. At the electrode, the copper ions turn into atoms, thus adding to the electrode. The copper electrode will slowly gain in size. Now, let's zoom out and talk about the function of the salt bridge. We have just seen that the solution on the left slowly contains more zinc ions. The solution now contains more positive than negative ions, so the solution would slowly build up a positive charge. The electrons, having a negative charge, would be attracted by this positively charged solution, thus preventing them to leave and travel to the other side. This is where the salt bridge comes in. Let's zoom in on the left side for a closer look. We now see more positively charged zinc ions than negatively charged chloride ions, so the solution now builds up a positive charge. If this problem is not resolved, the galvanic cell would not function. Therefore, this positive charge is balanced by negative ions from the salt bridge. In this example, a salt bridge has been chosen with a sodium nitrate solution, so the positive charge of the zinc ions will be balanced with negatively charged nitrate ions from the salt bridge. This way, the solution will remain neutral, and the electrons are free to travel to the other side for reduction. At the same time, also zinc ions will travel into the salt bridge to balance the charge. On the other side, there will be a similar challenge, because there the copper ions are reduced into copper atoms, and therefore positive ions are leaving the solution. The negative chloride ions remain behind, thus causing the solution to become negatively charged. This negative charge would repel the negatively charged electrons, preventing them from reaching the electrode. Again, the salt bridge comes to the rescue, providing positively charged ions balancing the surplus of negative chloride ions. In the example, positively charged sodium ions travel into the solution. At the same time, negative chloride ions will also travel into the salt bridge. This way, we have created an electrical current using chemicals. The same principle is applied in batteries, and just as a battery has a positive and a negative electrode, this electrochemical cell does too. To determine which electrode is the positive and which is the negative electrode, watch the route the electrons take. Electrons are negatively charged and thus travel to the positive electrode, which attracts the electrons. So the copper electrode is the positive electrode. At the zinc electrode is a constant production of negative electrons, which makes this rod the negative electrode. So when generating electricity, the side where oxidation takes place is the negative electrode. This is where the reducing agent reacts, here zinc. At the electrode where reduction takes place is the positive electrode. The emphasis here is on the words generating electricity. Some batteries can be charged, and when charging a battery, the process is reversed, and positive and negative electrodes are reversed. So when charging a battery, the side of oxidation is where the positive electrode is. At the top of the animation is a voltmeter. A battery or electrochemical cell has a potential. This potential can be calculated with the standard electrode potentials. Every half reaction has a standard electrode potential, and these values are listed in tables. These values are measured in volts under standard conditions. In this case, these values are plus 0.34 volts for copper ions and minus 0.76 volts for zinc. Subtract these values to get the potential of the cell. In this case, 1.10 volts. If you want to pause the video to make notes, use arrows to indicate movement of the particles. As a recap, on the left side, zinc ions enter the solution and nitrate ions travel out of the salt bridge to compensate for the positive charge. The electrons produced by zinc travel to the right side, and the copper ions leave the solution. These ions are balanced with sodium ions from the salt bridge. Pause if you want, and then we will look at 2 additional questions. Question number 1. Which of these electrodes could be replaced with a graphite electrode? A graphite electrode is an inert material, which means it doesn't react. Hopefully, you chose the copper electrode. On the left side, it is actually the zinc electrode itself, which is one of the reacting components. The zinc is required for this reaction. On the right side, the copper ions are reacting, and these ions could receive the electrons from a graphite electrode just the same. After a while, the black graphite electrode will slowly turn reddish-brown from the copper depositing on the electrode. Question number 2. What would happen if the entire left side of the cell is replaced by a silver electrode in a solution of silver nitrate? Well, the reducing and oxidizing agent have to be reviewed again. Now, the strongest oxidizing agent are the silver ions in solution, and the strongest reducing agent is the metallic copper electrode. Before the copper ions were reduced, now copper atoms are oxidized. Now electrons are produced on the right side, traveling from right to the left, where the silver ions accept them. On the right side, the copper ions are entering solution, and this electrode will diminish. On the left, the silver electrode will gain in size. Also, the ions from the salt bridge will travel in the opposite direction. Sodium ions travel to the left to balance the silver ions that left solution, and nitrate ions travel to the right to balance the copper ions. Now, oxidation takes place on the right, making the copper electrode the negative electrode. Reduction takes place on the left side, making the silver electrode the positive electrode. Also, the potential changes to a mere 0.46 volts. This concludes this lesson on the galvanic cell. Hopefully this video helps. Please like this video as it helps this channel to grow.